So in this video, we're going to talk about limit properties. And before we do that, I do want to show you the limit in all its glory, what it looks like. And there it is. So we have the limit of our function as x approaches c equals some number L. And I do want to talk real quick again about, well, what if L is infinity? And I want to do that with a graph over here. So if we look at the limits of this graph on the right, and let's take the limit as we go to 0 from the left, and let's take a look. So as we approach 0 from the left, we find ourselves at a height of 1. And that's that limit. If we look at the limit from the right, so here we are approaching 0 from the right, we find ourselves at a height of -1. And those limits don't equal. And so then we would say the two-sided limit doesn't exist. So we have a one-sided limit, another one-sided limit. They don't equal, so the two-sided limit doesn't exist. Now, well, how does infinity come into picture here? Well, infinity tells us a specific way that the limit is failing. So if we consider, say, 1 over x squared, and let's look at this function as it goes to 0 from the left. So if we follow the function along from the left, it's going to infinity. And the infinity is telling us here then that the failure of the limit is being caused by a vertical asymptote. And so that's telling us then that it's not this type of failure. This is called a jump discontinuity. I also like to call this a gap. There's a gap in the function here. But infinity tells us, no, the failure isn't a gap. The failure is a vertical asymptote. And if we look at the from the right, what the limit is, approaching 0 from the right, that's also infinity. So approaching 0 from the left and the right, they both go to infinity, which means then we could say the two-sided limit is infinity, since the left and the right are the same. So in my experience with math, that's why I think people prefer infinity. I tend to also prefer infinity, just because it gives us another piece of information on what's happening with the limit. However, it's fine to write this also as does not exist. And for our case here, I would say that does not exist is actually the technical answer. So what you're going to find with MyMathLab is sometimes you'll have a selection that says does not exist. Sometimes you'll have a selection that says infinity. And sometimes you'll have a selection that says does not exist or infinity. And this is also all meaning the same thing here. So I know that can be a little bit confusing with MyMathLab. And if you ever have any trouble with that, remember you can always hit the send to instructor, and I can check that out and make any corrections with that. So let's go then to the actual limit properties here. This part might be a little bit scary. And here are the limit properties. Now this is from your book. I think it's page 70. And there is another property here that I do want to list, I'm listing down here is number 8. Your book does mention this, but it's kind of off to the side, where this is actually a very important statement for us going forward. So these are the properties of the limit. They've been figured out for us already by other mathematicians, and we don't really have the tools yet to prove any of these. So you're just going to have to accept these as facts. They are facts, and by the end of test 1, you will actually have the knowledge to prove these. So if you're interested in that, something you can check out. You got to have a certain passion for math to want to get into the proofs. But I do want to give some examples of these. So let's check out number 1 and 2 here. And in general, what these two statements are saying is that the limit distributes. So this is something you're already familiar with, distribution. So if we have two functions being added or subtracted, and if we decide to take the limit of this, to any number, then the limit distributes. And we have this statement. And overall, that's what property 1 and 2 are saying here, is that the limit distributes just like how you're familiar with how distribution works. So distribution working just like how you'd expect it here with the limit. And that's what property 1 and 2 are saying here. So what would that mean? Let's say if we just threw some functions in there. So let's say we had x squared plus 2x. Well, the limit distributes. So we can just distribute the limit to each of those terms. And this makes, most of the time, things easier. It's easier to take the limit of something simpler. And the limit distributing allows us then to break this more complicated thing down into simpler parts, and then just add them together when we're done. Now, we haven't talked about how to actually do these limits. That's the next video on how to solve these algebraically. Just about the properties here. So property 3 here is actually something you're going to see through most of the, probably, well, all of calculus actually. This property 3 is in limits, derivatives, integrals. You're going to see this all the time. And what this one is saying, so things connected by plus or minus are called terms. Things connected by multiplication are called factors. So we have two factors here. And what this next property is saying is that if we have a constant factor, so k represents just like a number, it's just a number, we have a constant factor here, then we can pull that outside of the limit. So here is inside the limit. The limit, what's inside is what the limit is acting upon, inside the limit, and then we can pull the k outside of the limit. And all we have to do here now is just take the limit of the function, and whatever our answer is, we just multiply it by that number. So for instance, in this example right here, 2 is a constant factor, and so we can pull that outside the limit. So property 4 and 5 here are both also pretty interesting. And what they're saying is something similar to distribution, but instead of being plus or minus here, it's multiplication. So distribution is only for plus or minus. So multiplication is something different. This doesn't quite have a name, but I like to call this pass along. So we are taking the limit of two factors. We can pass along the limit to each of those factors. So for example, let's say we had x squared times natural log of x. So they're connected by multiplication. There are factors here. And so the limit will pass along to each of these factors. And then we can take the limit then of these factors individually, which again makes things easier. And property 5 here is very similar. We can pass along the limit to the numerator and denominator. So property 5 says that if we're taking the limit here, that we can pass along the limit to the numerator and to the denominator. And that's what property 5 is saying. So an example of that, let's say we had x squared over e to the x. Well, this limit property allows us to pass the limit along to each of these functions. And again, that makes things most of the time simpler. Usually simpler to deal with smaller parts than the whole thing. And then finally, these last two properties here, 6 and 7. For what we're doing in the book, all the book problems actually satisfy all the conditions here for 6 and 7. You're never going to see a problem that doesn't in the book, which overall means property 6 and 7 are basically the same for what you're going to experience in homework. And what I mean by that is, let's say we have a function and the whole function itself is raised to some power. Then what the property is saying is we can bring the limit into this parentheses then. And we can connect it right to the function. So definitely a unique property. Now there is a special condition on this, that n does have to be a positive integer. And same with 1 over n would have to be a positive integer. And what I'm saying is all the homework problems satisfy all these conditions. And what that basically means then is if you're going to take the limit of a function to whatever power, the limit will always pull into the parentheses. Now again, that may seem unfortunate. You'll never experience actually when these fail in your homework. And so it may be tough to remember in the future that there are these conditions here that n does have to be a positive integer and in these two forms. Overall, though, properties 6 and 7, we're not going to see too much this semester, though. Now, 8, your book does talk about, doesn't list it in this table, though. 8 is massively important for almost all your homework problems in this next section. And this one is saying that the limit of a polynomial is always equal to just that value c in the polynomial. So what that means is, let's say we have x squared minus 2x, which is a polynomial. And so this property is saying then, this limit of a polynomial is always going to be equal to what just plugging the value c in. So just like function notation. So if you're taking the limit of a polynomial, then this is just function notation that you're used to. That you're just going to plug c into the function. And now the huge caveat here, though, is it is only for polynomials. Well, other functions do satisfy this, but for now, this is for polynomials. Polynomials always satisfy this. So to finish up here, I just want to show some examples of things that are good to know. Not really necessarily properties, but things that can happen and are good to be able to identify. So here's another picture from your book. Actually, I think this is one that came from 2.5, which we'll come to shortly. And I just want to point out some things here with these functions. And if we look at picture A here, A is just a function. Nothing special there. If we look at B, it's got this hole here, and I like to call that a hole. This function has a hole in it. If we look at C, it's got a hole and a point. Now in this particular case, because the point is right above the hole, this is also called a removable discontinuity. And we'll see that again in 2.5. If you look at D over here, there's a gap. The book likes to call this a jump discontinuity. If we look at E, we have a vertical asymptote. And so the function is going off to infinity. Vertical asymptote. Book likes to call this an infinite discontinuity. And then finally we have the very unusual case of a function that has infinite oscillations that get squeezed into an ever smaller and smaller space. And that's sine over 1x in this case. And this is an oscillating discontinuity. And what's useful here is if you can identify these things, because these are common points of failure. And now we haven't talked about continuity yet, but this also does affect that. But it also affects the limit. So for A, the limit exists. For B, limits do exist at a hole. For C, the limits also exist at a hole and a point. For D, though, for a gap, the limit will always fail. For E, a vertical asymptote, the limit will also always fail. Again, we're into that question about infinity there, though. And then for F, at least if we go to 0, the limit will always fail. And so that's why it's good to be able to recognize these things. So if you can see these things, you'd be like, oh, well, I know the limit fails there. So for us, the limit fails at gaps, vertical asymptotes, and oscillations, infinite oscillations like this. And in the next video, we will put all of this to work then to solve limits algebraically.